we have been, as an industry, really unable to provide the design community and even internally understand what it takes to make sure we get the performance we need and assured for our customers. And so we put together the big DID program that Dave had given information to all our members with, and I thought it might be useful to give you a little update. I'm going to expand this update for the TNO, so you'll be able to get more of it then. One of the things we could do right away, we have over 20,000 data points for carbon steel. So this is WCX is for whether it's A, B, or C. So this is normalized and tempered typically. This is quenched and tempered. We got about 20,000 data points. One of the things we're trying to do is develop a series of carbon steels. Historically, when I started at Steel Founders Society, the notion was that as a Steel Founders Society, we needed to educate our customers so that they were capable of using steel castings. In the last 15, 20 years, Malcolm and I realized that we don't need to so much educate them. We need to actually make it so that they don't have to make decisions. We want to make it easy for them to use steel castings. That's why we developed ASTM A915 and A958 that uses the SAE AISI names like 1030 so that we didn't have to teach them that WCB was the same as 1025. Same thing with 8630. We don't need to tell them that that's A487 grade 4N. We can just tell them to order 8630. So one of the things we want to do in our industry is we want to make a series of carbon steels that are transparent to our customer base. So using this database, you can see that our customers really look for three flavors of carbon steel. One is 36 KSI, which is the old historic lower limit, and you can see we virtually always meet that. The common next generation of steel products that we don't have a standard for says that carbon steel ought to give you 42 KSI, and you can see that that's not a real challenge. And then the next generation says 50 KSI, and you can see about half the points are still higher than 50 KSI. So one of the things that we want to do is develop a series of standards so that people who are used to buying mill products and they want to buy a steel casting that they've designed because they've looked at additive manufacturing and they want some clever shape, we want to make it really easy for them to do that. So we've just proposed to ASTM a standard specification for structural steel castings that has 3 grades, and these 3 grades have exactly the same name as the most common mill product. So A36, ASTM A36, we call it C36, and it has exactly the same composition and exactly the same mechanical properties as A36 mill product. We do the same thing for C572, which is ASTM A572, grade 42, which means it's got a 42 KSI yield strength minimum. And we have exactly the same composition. We do bump the silicon up a little bit, but it's got the same composition and the same properties. And then the ASTM A992, we call C992, it has the same composition. And you can see that for both of these grades, to make sure that you can meet the properties, it's permitted to add vanadium or niobium in order to get the requirement up. And so you can see that we really can make the mill grades as cast grades if we get this. This standard also, we're planning to embed in it the first article NDT indications so that our customers don't have to make any decisions. They can just order to this standard without having to specify NDT or mechanical properties and have confidence that their arbitrary shape will work. The other thing we've done is this is for 8630. It's really for ASTM A487 grade 4A. We've been looking at using the data we have to come up with code allowable so that we can talk about what property you can use in design. Instead of giving people the ASTM minimum value and telling them to use half that number, we can give them what our actual property experience is. So we have like 8,000 points here. So it's really pretty straightforward for the 4A grade. This is the 4A grade. The minimum requirement is 60 KSI, but the average is 85, and 60 really is a type A design allowable. So you could actually get very close to the design allowable. This also shows you the compliance bias you get as you get close to the standard. We either retest, reheat treat, or reevaluate the test when we barely miss the requirement. So we see this kind of compliance bias in most of the things. This information is really going to be presented in Richard Harden's paper at the T&O conference if you're there. If you're not there after the conference, you can download his paper. But he's been using both Weibull statistics and the MMPDS, the old Mill Handbook standard, to try and validate lower bound design requirements. And so we're really beginning to get in the position, because of the data our members give us, to be able to communicate to the customers exactly how capable our products are. So I actually have been involved in a program with the Department of Defense trying to look at how, if you were in a forward operating base with the Army and you had a pile of scrap, how you would pick through that pile of scrap to make a charge to meet the mechanical properties that you want. Because of that, I've been using this data set. So I'm going to give you a little background on what I'm doing with them in terms of a project. And you can see that it should be really valuable to us as a steel founders group. Now, I put these nomenclature in. This is the handbook information for the correlation of tensile strength, UTS, with Brunel, Vickers hardness, and Rockwell C. So the little card you get from Wilson or the stuff you download from the web, that's what this is. So this is not really any data. This is what you find in those little handouts. And if you look at this, you can see that you get R squareds that are close to 1 because it's really tightly correlated linearly. You can see that Vickers and Brunel are close to the same. I use these symbols, and Dave came in and kicked me in the knee correctly because we've changed the nomenclature. So when you're given a hardness abbreviation, they all start with H. So HV is Vickers hardness. Vickers hardness is studied academically. So anyone that's doing research on steel is going to report their results in Vickers hardness. If you're making mill products, especially specialty tool steels, everybody uses hardness Rockwell C. This is the way we used to talk about it. This is the way we talk about it now, HRC. And in steel castings, we've always preferred Brunel hardness because our microstructure is coarse, large, and so you get lots of variation if you use Vickers hardness or Rockwell C. You have to take lots of measurements and average them. And Brunel hardness with a 10 millimeter ball averages it with the measurement itself. So we prefer Brunel hardness in steel casting technology. So if you really want to develop, old people like me know that the traditional way you developed a steel alloy was to pick the carbon content that gave you the hardness. You're going to lose 3 or 4 Rockwell C points when you did the hardness, and when you got the hardness target you had, if you quenched and tempered, you knew what all the properties were going to be from the hardness itself. And the hardness was really directly related to the ultimate tensile strength. So the UTS, or tensile strength, has traditionally been seen as half the Brunel hardness. So if you're young, or unfamiliar like me, you finally know that if it's 180 KSI Brunel hardness, then half of that number is going to be 90. So it's going to be 90 tensile strength. And so that's really useful. If I take all of the quenched and tempered data that our members have given us, so that's like 9,000 points, I get this correlation. So I get a 90% correlation with a 0.493 Brunel hardness. So it really is a good relationship. That's the way we traditionally did it. Today, we don't want to make any steels that are over 0.3 because they'll crack. If you want a piece of jewelry or you want to pay us extra, we'll make a 40, a 4140 or 4340 or an 8640. But typically we only make up to about 8630, and our sweet spot is right here around 25 to 27. So most of our alloy steels are really in this range here. We have a few where we're worried about weldability where we go down to 15. We hate going below 15. So this is the correlation of our data set the steel founders data set of Brinell and tensile strength with the yield strength. So I'm looking at what the yield strength is at a particular Brinell hardness or a particular tensile strength. And you can see how tight our large data set is. I get a 95% correlation and a slope of almost 1. It's 10% higher than 1 with yield strength. And yield strength is typically about 30 KSI below ultimate strength. And for Brinell hardness, I get almost at 0.5. So this is the data set we have. We have over 20,000 points for the carbon steel, 6,500 data points for the 86, and for the 43, we have about 2,400. So one of the main reasons I wanted to talk about this is to try and encourage other people to participate in giving us data and to show that we're getting real value out of this data. So we need to extend this to the 4100, to the CA6NM, to LC2-1, so that we can get all of this data. Now I'm using it at the moment. This is the WCB stuff. This is the average properties we have for the quenched and tempered materials. And then I can calculate the carbon equivalent in DI. And so if I want from that scrap pile to make something that's carbon steel, I'm going to shoot for a carbon equivalent in DI so that I can get the properties that I want. So if I take my data set of all the data, DI is the ideal critical diameter. It's a heat treatment idea of how thick the section can be and be heat treated into the center. It's based on chemistry. And so here is the chemistry calculation traditionally for the ideal critical diameter. And you can see that I get about a 70% correlation. And this is from chemistry alone without tempering temperature or anything else. So it's really pretty loosey-goosey, but I still get a nice tight correlation. Clearly you can see the 3 data sets. This is the carbon steel, this is the 8600, and this is the 4300. Carbon equivalent, of course, is a limitation we put on for weldability. It's also a compositional thing. You can see I actually get a nicer relationship with carbon equivalent rather than DI. I get a 75% correlation, and you can still see the 3 data sets. This is carbon steel, this is the 8600, and this is the 4300. We know that tempering temperature makes a difference, and so we really want to include tempering temperature in the calculation if we're going to try and predict properties from chemistry. We might even want to look at different tempering temperatures so we can select the one we want. And so even though I only get a 41% correlation because the chemistry makes a big difference, I do show that there's a real effect at tempering temperature. One of the interesting things in doing the background for this, people who calculate the effect of tempering temperature use the Holloman-Jaffe parameter, which if you're in the creep business, you know this is the Larson-Miller parameter. So when I saw that, I was confident that Larson-Miller must have invented it and Holloman and Jaffe must have stolen it to look at tempering. And that's incorrect. It's the other way around. Holloman and Jaffe invented it for tempering, and then the creep people stole it from them. So the Larson-Miller parameter was developed for tempering response for heat-treated steels. So if I include carbon equivalent DI and temperature, I don't change the correlation very much, but I get a fairly nice regression with that. You can see the carbon steel, and here all of the alloy steels fall pretty closely with each other. So I can look at all of that data pretty quickly. One of the challenges is when I look at R squared, this is how close all the points are to the line. All the points are to the line. This shows how far away on average the points are. This is in a fraction, so 1 would mean it's perfect, 0 means it's nothing, but it doesn't have units. This is actually in KSI. So if I can take the Brinell hardness, I have an 88% assurance that I'm going to get an accurate prediction. And in terms of precision, I expect any individual data point, one standard deviation is that data point can be 66% of the data points will be within 11 KSI of that line. So that's really a useful thing. For elongation, it's 72% or 0.72 as a fraction and 3.44. You can see that I'm not very close to the line, even though I have a higher correlation coefficient when I have this large data set. I get the poorest standard error. even though I get relatively high correlation coefficients. With tempering temperature, I only get 41, but I am only 15 ksi typically away from the line. And so if I look at carbon equivalent up here plus DI for this whole data set, then you can see that I get a marginal improvement, but not much. If I do it with a limited data set, and the reason I use a limited data set is because I only have 2,900 points with the tempering temperatures included. If I do it with that, my correlation goes down compared to this, but my standard error goes down much more dramatically. So if I want to predict, carbon equivalent plus DI plus tempering gives me probably the best correlation, and one of the nicest one is DI versus tempering temperature. So this is the kind of correlation that I'm planning to do, but this is how I put together the trial heats. And so I take this correlation matrix and I calculate the chemistry, and then I plug the chemistry in here. And so this spreadsheet is a spreadsheet that I'm developing where I can put my charged materials here, the composition of the charged materials here, calculate what the estimated heat composition is, get the carbon equivalent in DI, and that allows me for different tempering temperatures to calculate what I think the properties are going to be. And so I can look at different ways of predicting the properties here. And so my average properties are here. This is the actual heat properties that I get. And then these are the predicted properties using the different correlations we talked about. If I just look at correlations with Brinell hardness, I'm really not very far away, as you'd expect. The worst one is elongation, and John Griffin pulled these and said that all these specimens had porosity in the fracture, so they're not a good test for elongation. So I think the elongation stuff is pretty meaningless in this. This is the Dave Van Aken spreadsheet that's available on our website where I predict the hardness, and you can see it's not that compelling. But I'm going to be looking at that because I'm trying to develop this methodology so that I can put the best correlation up here so that you can, in your own shop, take your charged materials, put it on the spreadsheet, develop a heat chemistry, and then that will give you the carbon equivalent DI that you would expect plus the properties. And I think we can do that much better than we've done in the past because I have about 35 different, more modern formulations for carbon equivalent and DI. I've started doing the correlations with the different suggested or proposed DIs or carbon equivalents. And you can see that I get really relatively high numbers for the predictability, even for the elongation. And so I think there's a formulation in here I can use. And so with a bigger data set, I can make this even more accurate and precise. And so I want to get more data. And then my task over the next 6 months is to take each one of these and develop not only the correlation with the subsets of data, but with the data as a whole, and look at standard error to try and figure out which ones give us the most usable information. I can also say, instead of using the carbon equivalents that have been developed, I'll just develop my own. So I can take the chemistry and do a multilinear regression analysis. And if I use the chemistry data I have, I can get a 73% correlation and get my standard error down to 9 or 2.2. I have to really look at that. So I have to do a couple things. I need some data that I haven't used to develop the correlation and then predict to see how useful this is to validate it. So that's what my next step is. So with my chemistry, this is the correlation that you can see. This is the formula that I have from the data I have right now. That doesn't mean it's the best or the most useful formula that I'll come up with, but if you wanted to, you could plug the numbers in and see what you get. So with that, John is asking me, are there any thoughts on the potential to eliminate the need for physical testing with this? John, I think the only time that would work is when you have a significant amount of data on the same product set. But we have looked before, because there are European standards where if you can prove for a particular heat and heat treatment, you're in statistical process control, you can develop a sampling plan and verify compliance based on that sampling plan. We've never done that in North America, part of that is because we have more attorneys than they do, and that we have a lot of litigation. But the other reason is we historically did the mechanical testing because we didn't have good chemistry numbers. So it would take a really smart group of customers with us to agree that we could eliminate that. In our bigger DID program, we're really looking at, are there better tests than tensile or Sharpie? So just to spend a moment with you, we've been looking at microstructures of steel castings, and for typical microstructures like you would find in a keel block, we have second phase particles and porosity that are on the order of 1 millimeter in diameter. The tensile specimens we use are 13 millimeters in diameter. So if I happen to have one of those 1 millimeter features, or two of them together, or three of them together, I compromise a great deal of the cross section that's being tested. And so as my steel gets stronger and lower in ductility, those second phase particles and porosity limit my ductility in a way that's not true about the component I'm making. And so one of the things that we've asked Charlie and John to look at, and the people at Texas A&M, is should we be using a different size mechanical test in order to get usable information? And if you thought that the tensile test was a problem, the Sharpie V-notch test tests an 8 millimeter by 10 millimeter plane. And so that's why you see such a high variability in Sharpie V-notch. So maybe we ought to be looking at a different test like dynamic tear, but that test is a lot more expensive and very few people are set up to do it. So is there a better notch tensile bar or something else that would give us toughness, or at least elastic plastic measurements, so we could use it in design? So this is part of our great big DID program, trying to wrap our arms around how could we really characterize the mechanical performance to give our customers assurance of performance. But with all this statistical data, we're beginning to at least get the raw data we need to have the conversation in a meaningful way with customers.